All right, let's do an example with this length contraction. A crew member on a spaceship traveling at 0.99 c relative to Earth measures the length of the spaceship to be 400 meters. What length do observers measure on Earth? And again, here's the procedure, right? Similar to what we had before with the time problems. Okay, so what are the two reference frames? Well, there's the moving spaceship, and then there's the Earth. So spaceship and Earth. Okay, who or what measures the proper time? Remember, who or what measures the proper time? The astronaut. Agree? Because the spaceship is not moving relative to the astronaut. The astronaut's inside the spaceship. So who measures the proper length? The astronaut. What is the proper length? Well, it says it right there, right? The crew member measures the length of the ship to be 400 meters. So that's the proper length. So the proper length, lowercase l, is 400 meters. Okay, who measures the contracted length? Somebody on Earth. Okay, and so now we got to figure out what it is. So again, here's the equation. Right there, right? So we have L prime, contracted length equals proper length divided by gamma. So it's always going to be smaller, right? The person in the Earth frame is always going to measure something smaller. Okay, so just like before, gamma 1 minus beta squared, negative 1/2 power, 1 minus 0.99 squared minus 1/2 power, 7.089. So therefore, L prime equals 400 meters divided by 7.089, and that's 56.4 meters. Okay? So the astronaut inside the spaceship says, my spaceship is 400 meters long. But we, on Earth, we don't measure that. We actually measure the length of the spaceship to be contracted to 56.4 meters. That's relativity. And again, why don't we ever notice it? Well, that should be obvious by now. Why don't we ever notice it? Because we're down here, right? If we could actually make a spaceship that goes to these crazy speeds, then we're going to start noticing it. Okay. Let's do another one. An astronaut in a rocket passes a meter stick moving parallel to its long dimension. The astronaut measures the meter stick to be 0.8 meters long. How fast is the rocket moving with respect to the meter stick? All right, so same method to work this thing. Okay, so this is a little bit different, right? Because now there's a meter stick out in the middle in outer space, and the rocket ship is passing the meter stick. All right, and now they want to know how fast the rocket is going. Okay, so that really means figuring out gamma, right? Because gamma has the speed in it. Okay, so what are the reference frames? The spaceship and the meter stick, right? Earth's not important anymore, right? So reference frames, spaceship, and meter stick. Okay, who or what measures the proper length? The meter stick, right? The meter stick. The reference frame of the meter stick. So therefore, what is the proper length? Well, it's a meter, right? So the proper length is 1 meter. Okay, who measures the contracted length? Well, who's moving relative to the meter stick? The astronaut. So the astronaut measures the contracted length. What is the contracted length? Well, they tell us, 0.8. So they say that L prime is 0.8 meters. Okay, so all right, so we want to know the speed. That means you calculate gamma. That means then you calculate beta. So it's a little kind of, anyway, whatever. All right, so just use this. So gamma equals L over L prime. So 1 meter divided by 0.8 meters, and that's 1.25. Okay, then it is, so then again, gamma is 1 minus beta squared, negative 1/2 power. So therefore gamma to the negative 2 equals 1 minus beta squared. Therefore, beta is equal to 1 minus gamma negative 2 to the 1/2 power. And then you just plug it in. You just plug it in, and I promise you, you'll get beta to be 0.6. All right? So what's this? Remember, beta is V over C, right? So that's 0.6. So therefore, the velocity is 0.6 c. Okay? So yeah, so make sure you can, do all that algebra. Okay, this is a really awesome video clip. We're not going to watch it. This is for you to do. So this would be a great time, students, to pause your video. It's called minute physics. So they have a minute to explain something, and they usually do a really good job. So this is time dilation and space contraction. So they talk about time dilation, which we talked about earlier, that Mount Washington experiment, and they also talk about space contraction. And so make sure you watch it. It's only a minute. It's really super wonderful. All right. Now sometimes we're going to have a problem where they don't give us the proper time, or they don't give us a proper time. And so what do? You can't just quit. So let's learn about that. So what we're going to learn now is something called a space-time interval between two events. Now remember, space-time is the position, x, y, z, as well as the time. So it's 4 coordinates, right? That's what we mean by space-time coordinates. Okay, so let me just erase this. Okay, so look at that slide. And this is nothing new, right? So here's a line or a line segment, right? And this is length d. Okay, so this is delta x, or this is delta x, and this is delta y. So how do you get d? Just use Pythagorean theorem, right? So delta x squared plus delta y squared is d squared. Okay, no kidding. Now, what we want to do now is we want to change our reference frame. So we're going to just so here's our y, here's our x. We're just going to rotate it. I don't remember if it's this way or this way, but who cares? We're going to rotate it. We're going to change the reference frame. Okay, whoopee. So you change the reference frame. Oh, there it is. Okay. So here's our old y-axis. Here's our old x-axis. Now this is our new y-axis. This is our new x-axis. Okay. So now here's d. So according to our new reference frame, this is delta x prime, and this is delta y prime. And so as always, delta x squared plus delta y squared equals d squared. Okay, no kidding, right? I mean, no kidding. I mean, should the length of an object depend on the reference frame? I mean, I'm just saying, on the coordinate system, right? Should the length of this depend on the coordinate system? No, of course not, So here's a term for you. We're going to say that d, maybe I have it written down on the slide. Yeah, good. So we say that d is an invariant quantity. An invariant quantity. But physicists are lazy, right? So we just call it an invariant. Okay? So an invariant is something that doesn't change when you switch coordinate systems. Okay. Now, let's go back to the light clock. Okay, when we first discussed the light clock, we had Velma, according to Velma, right? And then we had what Velma looked like according to Mort. So we just had 2 reference frames, right? Well, now let's add one. Okay, So now we have 3 reference frames. So we have S, you know, S is, right? And then here's S prime. That's what we discussed earlier. Now let's say we have another one, S double prime. So S double prime is moving relative to S, okay? Whatever. All right. Now remember, this is, you know, this is 150,000 kilometers, right, from one mirror to the other one. So that doesn't change, right? That doesn't change. So what's the only thing that changes? Well, you know, this distance here, let's see, from here to here, that's delta x prime. But then for this guy, for this rocket ship or whatever for reference frame, this is delta x double prime, right? Okay, so here, let's just solve for h. So we'll have h in the s prime equals h in the s double prime. So what's h in the s prime? It's that squared minus that squared. So it's 1/2 c delta t prime squared minus 1/2 delta x prime squared, right? That's what h is in this reference frame. Okay, what is h in this reference frame? Well, it's just hypotenuse squared minus that squared. So it's 1/2 c delta t double prime squared. Whatever. Minus 1/2 delta x double prime squared square root of. Okay? Now, let's square both sides. And let's get rid of all those 2's, right? Just multiply everything by 4. Okay. So, oh gosh. All right. So, there you go. Okay, there you go. I mean, that's not all that wonderful. Now, we usually like to write it just a little bit differently. You'll see why in a minute. So I can do that. I'll just pull the c outside. Or the c squared, actually. Okay, all right. So you notice that this is this quantity that's in frame s prime, and this is the quantity in s double prime, right? So it doesn't appear to change. So we would say that this is an invariant, right? It's an invariant. Okay? So what we want to do then is we want to define something called the space-time interval, S. So the space-time interval S between 2 events. And this is how they define it. Now, it's kind of weird, right? I mean, it's called the space-time interval S, but they define it with S squared. Well, whatever. Okay, so this thing here, this is called the space-time interval between 2 different events. So for the light clock, it's the space-time interval between the photon leaving and then the photon, you know, returning. Right? Anyway, now you say, who cares? Right? What good is this? Well, we'll see in a minute. But all I'm saying is this never changes from one reference frame to another. It never changes. So that's important, all right? So c squared delta t prime squared minus, I can just do that, minus delta x squared equals constant. All right, space-time invariant. Never changes. And it's kind of cool, you know, because it has time in it and distance. So that's why they call it space-time interval. You know, it's just not the time interval or the distance interval. It's both. It has time and distance. So that's why they call it space-time. All right, now, what good is it? Oh, yeah, sorry. Okay, so here it is. All right, so s squared equals all this stuff. Doesn't matter what reference frame you're in. It's constant. It's an invariant. Okay, now we want to see why we're so excited about it. Okay, let's read this thing. A firecracker explodes at the origin of an inertial reference frame. Then 2 microseconds later, a second firecracker explodes 300 meters away. Okay, so this is at time equals 0. This is at time equals 2 microseconds. Astronauts passing in a rocket. Okay, so astronauts in a passing rocket measure the distance between the explosions to be 200 meters. So they, so they say it's 200 meters according to them. According to the astronauts, how much time elapses between the two explosions? All right? So this is one reference frame, the reference frame of the Earth. This is the reference frame of the rocket ship. Okay? And so what we want to figure out is what's the delta t in this reference frame, you know? Or let's call it delta t prime or something, whatever. Okay? Now, you say, piece of cake, right? Well, let's see. So number one, what are the events? What are the two events? Well, the firecrackers exploding, right? So firecracker, what do you call it? Exploding. And again, there's two of them, right? There's two of them. Okay, now, sorry. And what are the reference frames? Reference frames. Well, there's the Earth and the rocket. I mean, what else is there, right? There's the Earth and the rocket. Okay, now here's the problem. I mean, we want to find time, right? It says how much time elapses between the two explosions. So, you know, we kind of go back to what we've learned before. You know, proper time and dilated time and all that. Which reference frame measures the proper time? Well, it can't be the Earth, right? Because this location is the first explosion. That location is the second explosion, so it's different locations. It can't be the astronaut because the astronaut doesn't see the explosions happening at the same location. So we're dead, right? So we're up a creek without a paddle, right? Okay, so who measures the proper time? We don't know. Okay, we don't know. Well, I mean, so what are you going to do? The only thing you can do is use the space-time interval. I mean, that's all you can do. Because, you know, the space-time interval relates the measurements of space and time in one reference frame to another reference frame. So that's really all you can do. You can just use that. So let's try it. All right, here we go. So let's call S Earth, like we always do, right? So S is Earth. Okay, so the delta t is 2 microseconds, and delta x is 300 meters. All right, the S prime is the spaceship, or whatever, rocket. And we don't know what the delta t prime is, but we know that the delta x prime is 200 meters. Okay, so then you just have to plug it in. So you just have to use that. So c squared delta t prime squared minus delta x prime squared equals c squared delta t squared minus delta x squared. I mean, and what we want this, right? We want delta t. So you just get all that other junk over there. So c squared delta t prime squared equals c squared delta t squared minus delta x squared plus that, right? Plus that, plus delta x prime squared. We have to divide by the c squared. Then we have to square root it. And I promise you, you do that, you get 1.86 microseconds. Okay? So, what's the moral of the story? When you get a problem and it doesn't, you figure out the reference frames and the events, and there's not a proper time or a dilated, there's not a proper time, you have to use this. That's all you can do. You have, or if there's not a proper length, you have to use the space-time interval. Okay, let's quit.